Hello guys, I'm Sridhar Mukherjee. I'm a machine learning researcher at Penn State. Today I'll be discussing why residual networks, rather ResNets, are super interesting in the way like what problem it solves. I will be reading to the paper and showing you main points in the paper that directs towards that understanding. Actually, I believe that ResNets are more powerful than you think. And I will show you one follow-up paper that came up in NeurIPS, I guess, which shows you the power of ResNet, the mathematical power too. So of course, we will be doing the coding of ResNet after this video, but this video is dedicated towards understanding, towards exploring why ResNets are powerful and what problems do it solve. And also I will end it by helping you understand the the coding aspect a bit of how to build it from scratch. And then in the next part of the video, I will be teaching you how to code it from scratch, taking those components that I discussed towards the end of this video. So the paper the residual network's first paper name is Deep Residual Learning for Image Recognition, as you can see on the screen. So let's discuss what it solves. So first of all, you can see on the screen, essentially it solves the very fact that how to build more deeper networks, like by stacking more layers, that you can see. So the basic idea is that when you stack more layers, when you make more deeper networks, it results in a problem called the vanishing gradient or exploding gradient problem, which is nothing but, if you have read recurrent neural networks, or uh, let's think in this way, like a lot of neural networks stacked, and if the weights are continuously greater than 1, so if the weights are continuously greater than 1, let's say they are wi, so then w to the power n, where n becomes large, this almost converges to infinity. And if the weights are consistently less than 0, then w to the power n goes to 0. So these are called exploding gradient and vanishing gradient problem. Now, naturally, this hampers convergence, because the optimal thing is not reached, because it's either the weights are all becoming 0 or becoming infinity, or oscillating between that. So what happened that after that, as you can see on the screen, there are some batch normalization techniques. Hey, and other great researchers of deep learning have introduced certain initializations, and also then batch normalization came in. So however, and they have compared with something called VCGNet. But then when the deeper network started to converge based on that, there's initializations and normalization layers. Layer normalization, I'm not sure whether it's batch normalization or not. I think it's layer normalization. Also, I believe it's batch normalization, because they have used batch normalization in this paper. So what happened is that there's a problem called degradation problem that came in here. What is a degradation problem? It shows that uh, when you build a deeper network, after a certain iterations, the training keeps on decreasing, but the tests doesn't decrease and it becomes saturated. And they said that it isn't caused by overfitting, because because that's the whole problem that is being solved by the previous thing. It doesn't cause overfitting, and they say that it doesn't cause overfitting, and the accuracy gets saturated in the test portion. Now, why they think, they are sure that they have shown by experiments that it doesn't cause overfitting. Okay, but the question is that, because number one reason it doesn't cause overfitting is that the test accuracy is not decreasing. It's just become constant, right? Because for overfitting, there needs to be let's say, the test accuracy should decrease and the training accuracy should increase, right? There should be a divergence, balloon-like structure that happens, but it converges in this case, and that's natural because of the batch normalization and other stuff. But the interesting question that comes up is that why this is doing that, and they investigate this factor, and they think that is something called degradation problem. What is happening? And this, I believe, this is the most important part of the paper, like the conceptual part of the paper, which I think people may miss. The people just may think about, oh, it's residual learning, X is added to this. But why X is added to this? This is very important. Why do they think that X is added to this, and why do they think, and what problem does it solve? This is the paper, and also I will show up another paper that solve this issue. So what they think is the following: is that so what they're doing is that they are trying to learn this final hx. Let's say this is the mapping they are trying to learn. But what they're doing, instead of learning it directly, what they're doing is that they're learning it as first fx and then plus x. This is the hx. Now, why does it help? Like, why does this actually help? This helps because they realize this is, first of all, called a skip connection or residual connection or identity mapping, whatever you call it. Uh, so X is, it's this kind of thing is done in classical machine learning, in kind of, not exactly, but kind of in boosting algorithms, where uh, the error is added, uh, and the error is learned. I'm not sure. Yeah, it's boosting only. Yes, the boosting algorithm where error is added. Now, the question is that it's similar to that. Rather, they are trying to learn the residuals. You may think like this, but it's far more it has a far more deeper implication. And if you read through the paper, I have just marked out these important aspects, which you can later revisit. But what I will tell you is the following thing: that what exactly they are learning. Now, what they're thinking is that when a deeper layer is constructed, um, the initial layers are actually probably learning the identity map X. Just they're trying to learn the identity map because they think that that's what the hypothesize. For example, you can see that if one hypothesis is that the multiple nonlinear layers are asymptotically approximating complicated functions, which are this is still an open problem during that time. I have to check whether it's still an open problem now, but we have proved that. I mean, they have proved that yes, a hidden layer can layer with a nonlinearity can approximate a function quite asymptotically quite well. But I'm not sure whether they're talking about this or not. But let's take it for granted that um, let's take the hypothesis not for granted, but let's assume the hypothesis that it's multiple layers actually asymptotically approximate the complicated functions. Then it's saying that it can actually also asymptotically approximate hx minus x, right? Hx minus x. If because they lie in the same space, kind of thing. If they can learn hx, then surely it can learn hx minus x, because they have this they can be smooth, they can be differentiable, continuous, whatever they need for the proving here in this case. Now, what they're saying is that probably in multiple layers, when they're learning the identity, they are trying to find the identity map. And the weights in the first initial layers, or let's say a certain block, cannot really learn that identity map really well. So probably actually the function is trying to, like, the model is trying to learn the x function, fx is equal to x function, but somehow the weights are not being able to learn that. And they have proved in certain way that why they are not being able to learn that by empirical reasons. But basically is that they are not being able to learn the identity function. So what they did is that they have empirically observed this. What they did is that's why they added an x identity map after every layer, after a sequence of layers like this. After a sequence of layers like this, initially it was x, and they have learned, again added x, and here they have learned f of x. And they are saying that, oh, I am learning fx plus x, which is equal to hx that I have showed before, right? Now, they think that sometimes in deeper networks, this is actually zero, right? They're trying to say that this is actually zero, or they're not changing much. The standard deviation is less, let's say. Let's say it's just a constant also. And the model is probably, since it's a nonlinear network, it's really taking hard time to find a linear network outcome. Let's say c plus x. Okay, it's taking some time. It's like you're using sine x and cos x to find it, to approximate x, right? Because they're highly nonlinear. You're trying sine x and cos x to approximate x. So that's where the like alpha sine x plus beta cos x, and that's where the model is trying hard to find that alpha and beta, let's say, or whatever sequence of it. It's like using a gun to shoot a mosquito, right? In that, there's a proverb like that. So they what they think is that if they have observed empirically by graphs that, for example, in this graph they have shown that the layer responses, the layer widths you can see are constantly for the non-dotted layer, and for the non-dotted indices or whatever you can see here, all the resonets are actually very low, are lower than the corresponding plane without the residual aspect network. So what they're saying is that that skip connection, that residual aspect, uh, they're saying that since the standard deviation is low, that means probably the weights are similar. And if the weights are similar, they're kind of learning a constant function, which is hard, and that's why you see so erratic movement in the plane networks, because they're not being able to understand what's happening, and they're confused, and that's why the standard deviation is high. And this is what the hypothesis, and it's really working well. So what they added is that they added an extra x layer to make it understand, to make the model understand, hey, you can just make it zero, make it all the width zero or constant, and then you can add it because x is already there for you, right? So what they're doing is that they're making the model learn a constant function or a zero function, and just by, I think it's very, I mean, the model is, it's like explicitly telling the model that here is x for you. You just learn the constant or zero out there. Okay. And that's your job. You do not have to like, it's like understanding what the model is doing wrong and then adding it to the model. I think neural networks are much like babies. So you just explicitly tell them what to do and it will do well. Otherwise, it will not do well sometimes. So this is how I perceive it. So now this is about the innovation in this paper, the conceptual innovation in this paper that you can see. And this is what it is written in this blue and the green part. I'm not explaining it in details. The question is that how do they improve the architecture? They improve the architecture in this way that, so how they are defining it, this y is this new output, which is nothing but the filters, the convolution layers with the corresponding weights, and this extra added x that it has already started with. The diagram is pretty self-explanatory, and you will see it's pretty easy to implement, not hard at all. So it's like this. Now, often the question is that what if after this filters, because convolution layers reduces the dimension of the image. So what if this f is this output of this f is not of the same dimension as the input image or input or the input of the layer, not the image, let's say, input feature. So what they're doing is that they say that, okay, if it's the sizes don't match, it can be done in two ways. It can be done by a linear projection into that. So it's like, let's say the input size comes out to be let's say here it's 512, and after the input it's, let's say, 400, let's, for example, and you cannot add it here, the output, because here you have to add 512 and 400. So what they do is that they reduce this 500 to 400 level, they keep this 400 and then they add it, and that's what the whole purpose of, that's a linear projection, right? A matrix can transform a dimension, or like a matrix from, let's say, 500, a matrix can take 400 this times, you can take a vector of this to get a vector. The output will be, let's say, v dash of 400 cross 1. So that's what this whole map is doing, a linear map. That's called a projection, and projection to the space. So that's kind of linear algebra input out there. You should read about it if you cannot understand. And yeah, that's kind of interesting. And then comes that they are taking the basic aspect of the VCG net, which they have told what which is VCGNet is all about, but you can read about it, which is in it VCGNet in the corresponding VCGNet paper. But what they're saying is that their model have fewer filters and field like complexity, the number of layers are less. And this is the model. Now, I think you have all understood what um, the main aspect of the paper is. Main aspect of the paper. I believe the main conceptual aspect of the paper is this, that you are learning, uh, like it's like when the model is trying to learn identity map in actual, the deeper networks fail. And they have seen that for deeper networks, some of the layers are trying to learn the identity map, right? Um, and in that case, the model fails because you're trying to approximate in deeper networks without the residual aspect, just like linear convolution layers after layers after layers. And it fails because there's a lot of nonlinearity, and you're actually using a sequence of nonlinearity, a large sequence of nonlinearity to approximate linearity, which is failing, and that is confusing the model, and hence the weight are varying too much. That makes the model unstable after a certain time. And that's why they're adding a residual aspect to make the model expertly learn that, oh, if you're actually learning the linear thing, then just learn the weight zero out here and I will add x for you. If it's not linear, then by that approximation theorem, it can approximate anything. So with the assumption and with this heuristic idea, they show that actually this works. But what I will do is that before I go into the architecture and the implementation details, what I will show you is another paper, that is this. Well, I will show you one more mathematical aspect, is this, that why uh, also this whole idea of ResNet can also solve gradient, the vanishing gradient problem. And the reason is this. Let's say you have one layer. Let's talk with respect to one or two layers, one layer and then this layer and then final layer, and this is a loss function. The output of this layer is this, the output of this layer is this, and then based on that, you're taking the loss function. To calculate the loss function, you first have to calculate, you have to take, by doing that propagation, you're actually calculating the gradient of this del L dex not del L del x naught. You want to find this actually, because without finding this, you cannot find the derivative of the loss with respect to the widths, which with which you're actually trying to minimize. So if you want to take this, then you see that you use chain rule to do del L del x1, the back propagation part, times the del x1 by del x naught. So the good part is that this x naught is actually added here, right? So you can see that x naught is nothing, x1 is nothing but some x naught plus f of x naught. If you observe this, this is the one, because of the residual aspect. And since this is added, so if you do del x1 by del x naught, it comes out to be 1 plus, of course, f dash of x naught, right? Now what it does is that if this is too low, then it actually vanishes the gradient, um, the vanishing gradient problem also. But you can say it can have, um, it also depends upon the sign and all these things. You also take ReLU out there and all these things. It's just a basic understanding. It's not fully mathematical. What he says is that at least it can also, instead of this being very small here, it's actually multiplying 1 plus something, so it will never be 0. So that's what they're meaning. And but yeah, you can say if it's always greater than 1, it introduces the vanishing gradient problem, the exploding gradient problem. Yes, all these things are there, but let's not, because deep learning is not too very mathematical, because it's like an architecture based. I believe it will be soon very mathematical step by step. But what I think is this, that this is already being solved by the normalization methods and initialization methods, so it doesn't need to be uh, implemented. Like the vanishing gradient problem, exploding gradient problem are already solved. This is just a icing on the cake. Even if it does do the exploding gradient thing, the normalization and initialization will actually solve it. So this is just to show as an educational aspect, that for just your understanding, that actually it's kind of how the vanishing gradient problem, exploding gradient problem works. And this is maybe solving one of the issues. Yeah, it's all maybe out here, because you can only validate experimentally, empirically. Yes, so yeah, a bit more mathematical things are being actually addressed in two books. One is the deep learning by Bishop, which is relatively new book. And also there is another book called The Geometry of Deep Learning, which is pretty cool. I really like it, and it has more mathematics than any other book of the deep learning aspect. In fact, it is proved that I have posted on LinkedIn that mm, uh, it is proved that ReLU actually ensures um, good convergence results, and ReLU probably is one of the unique functions, activation functions. Yes, to understand this talk, of course, you have to know a bit of deep learning. If you do not, please read the books and then come back and learn this and hear this video. I mean, watch this video. Um, now the next part is telling you also another conceptual aspect of the ReLU thing, which is this paper. So this paper came out in, I believe it came out in, let me just check. I think it came out in ICE MLR, PMLR, that conference. And this actually shows, this is an interesting thing. So ResNet is actually told to be a solution to the shattered gradient problem, right? Now, this they ask, but they didn't explain what is the problem. But this paper is very creative, and also the topic, the title suggests that they shows you, actually tell you that if result on the answer, result really solves the issue, right? Then what is actually the question? What is actually the shattered gradient problem? The author in the actual paper didn't explain what is the shattered gradient problem. They gave a hint at what may be happening. But what this paper does is actually mathematically explain what is the shattered gradient problem. And it's really mathematical, and any statistics or a mathematics student or a probability student will really love it. I loved it too. So what they're showing is this, that if you remember that they're trying to mathematically formulate that aspect, that why, what do they mean by the weights doesn't change much, the weights remain same, and the standard deviation actually oscillates a bit. Standard deviation is not like constant, rather it's the standard deviation are not like constant. So what they're trying to say is that what they did the following experiment. Did a basic experiment. They took in a fully connected layer, and they gave an input. Let's say it's one-dimensional. They took one-dimensional experimentation so that they can visualize it, and they perturbed the input a bit to see how the weights perturbed. So they calculated this, how the weights change, how the function output change with respect to, rather not the function, not the how the weights perturb, but the how the function output change with respect to a small change in x. And what they found out is that the gradient of how the function output change, not the function, not the widths, but the function output change given the small perturbation in x, is this, that they found that for a fully connected, deep fully connected layer, like for a lot of layers, 24 layers, they have found that the change is pretty like a white noise. But in other case, for one layer, for a short layer, it's pretty, it has some information for but in case of a ResNet, it shows that it's not like a white noise. It has some really interesting inputs. They have some, how do they know they have some really interesting input? If you know time series, they have shown that the autocorrelation is not like, drops like white noise, because autocorrelation has no information after some time, right, to the next time point. So they are showing that like brown noise is really what has some information. So what they're showing is that the autocorrelation of this is, and they proves mathematically that is not like white noise. It has some information over time, and therefore the output, the way it's actually the model is learning something. It's something interesting, unlike the white noise, that even enough perturbation of the input keeps it white, doesn't change it much. It has a white noise out there. So essentially the weights are nothing but white noise. The model is nothing but not learning anything significant, and that's what they call that shattering gradient problem. You have to read this in a much more details, mathematically understand it, but this is the shattered gradient problem. What they're seeing is that as the deep learning, as a number of layers increase, the the change in the weights, the change in the function outputs at intermediate weights, intermediate layers are actually not informative. And probably that's one of the reason is that um, as they have told in the actual paper that essentially it's trying to learn certain very easy functions by a very large number of nonlinearity, which is hard to do, which is extremely hard to do. Um, the model is finding hard to do. So that's why they add one residual aspect plus X. I hope you understood this. This is what was the main aspect of the paper. So now coming to because we will be learning how to code it from scratch, but I believe that knowing this aspect will help you understand that how to do it and rather motivate or inspire you to do this, that this is something really new. Now how the whole architecture works. The whole architecture works is that they have taken a 34, so there are 34 layers of there are different layers of neural network, like ResNets out there. One is 18 layer, one is 32 layer, 34 layer, one is 50 layer, 101 layer, 152 layer. It's a lot of deep. And by taking a lot of deep networks, they've actually shown that this residual things actually work empirically. Again, everything is shown empirically. Nothing is shown mathematically. Now, we will talk about what is the network they have proposed and how they have proposed it and how we can think of doing it in a code. I will repeat it once again when I do the code, but I will repeat it now also so that it's twice the learning. So let's talk about this 34 layer thing. They have taken a 34 layer plain network without any residual thing. What they've done is that first they have done a basic convolution. And the stride is two. We will talk about this when we code together. Now they did a pooling again. It divides, if you can see, striding 2 and pooling with another stride 2 all divides the length by 2 because they're taking at the length of interval 2. So essentially after convolution or max pooling, the image size will decrease. And then you can see the image size constantly decrease, but after every 2 convolution blocks, just like this image, after every 2 convolution blocks, they do this with every 2 convolution blocks consecutively, they do this this residual addition. Now there are two things. One, this is for 34 and 50, and this is for 100. Sorry, this is for 18 and 50, 1834 layers, and this is for 50, 101, and 152 layers. So here there are three of them. Here there are 2 of them, and here there are 3 of them. Now observe how they do it. This is very important. Let me go to the picture once again. So they do this. This is for 34. So they take this, like this convolution, this thing 3 times. And again, they take this one, this residual blocks 4 times. They again take this residual blocks 1, 2, 3, 4, 5, 6 times. And again, they finally take it here 3 times. So essentially, these residual blocks are being repeated each at a very regular interval, and that repetition is total number of layers. For example, you can see how they count the number of layers. This is the residual block, let's say. This is the residual block, one residual block, and it's 3 plus 4 plus 6, 13, and 16. And each one of them is 2 layers, right? So 16 into 34, and these first 2 layers are makes total 34 layers. 32, 16 into 2, 32 plus 2 layers is the 34 layers. Now, how do they do it actually? So each of this blue thing is a residual, is a residual network, like I have shown here. In the higher in the higher number of layers case, it is being replaced by this. So when you make a convolution layer, you must understand, when you make the coding of the convolution layers, you must understand that this residual block is a very fundamental part. So therefore you have to draw it somewhere. So there should be one class, one object that does that. Okay, so let me write it down here. So this I have written for my own understanding. So there should be one class for residual block, because you understand that is being repeated all over again. So how do you make classes and objects in PyTorch based on what you see in the, like, how to recreate from scratch? You see that what is being repeated out there. So residual blocks must be one of the fundamental block and it must be repeated. Now, what else? You see that the number of layers out here, right? How many times it be repeated. So there should be a one aspect of number of repetitions, how many times it's repeated, right? For example, in this case, it's 3, 4, 6, 3. That's that many times it repeated, right? Now then comes the next aspect of, so of course, these two basic layers will be there. There is no, new classes that need to be formed. But to code from scratch, you need this thing that you need this residual blocks. Each of the residual blocks, a number of repetitions. But there are also some other nuances. What are the nuances are there? So you can see here it's 3, 4, 6, and 3 here again. But what other nuances are there? Certain nuances are there. One nuance is in the first case, there is no downsampling. What do we mean by downsampling? You can see that not downsampling. Let's say what it means is that in this case, in the dotted case, there is a stride by 2. That means this, since there is a stride by 2, what happens is that the dimension decreases. You can see becomes from 56 it becomes 28, and after regular the starting of each of these blocks, the dimensions decreases. You can see the skip connections are dotted. What it means is that here the dimension decreases, but here it was 56, so it has to be downsampled. The x has to be downsampled, and so that you can add, and that's where you can see that it can be downsampled using projection, or the actual thing can be padded by 0 and then added to the actual one. How they do it, it's there in implementation thing. They have done some experiments to show that which one works best, and rather they have seen that this which of the projection of the padding, which one gives better result, and they have seen that none of them gives none of them actually, like all of those things actually doesn't are very close together, close by nearby in the values, and it doesn't actually solve the shattered gradient problem. Okay, so what they did is this, that they uh, so understand this very carefully. There is a dotted part. That means here at from the apart from the first layer, from the next layers, there's a downsampling happening. Like it's halved. The image, the filter size is halved every single time. The feature size, and the x is added to the final output. That needs to be downsampling. That's why dotted things are there, and it is continued. So therefore, there is one extra aspect of what is called in which blocks there is the downsampling. Which blocks? For example, the second block, the third block, and the fourth block, right? If you consider each of these as the blocks, where the downsampling is happening in the second, third, fourth, at the starting begin point, the downsampling is happening, right? What else is there? Another thing is there is that in this case, all the output layers are 64, 64, 64, 64, right? So you have to also mention that at each of these blocks, when you say each of these blocks, what are the filter size, number of filters? So 128, 256, 64, all these things, right? So you have to mention these things, and you can see that here is 64, 128, 256, 512, again 64. And now inside of this, there is 64, 526 in the 50 layer and 101 layers. So one thing you can see that you can easily, if you just code this blue and this blue, and with some extra parameters like this, you can actually build a whole thing, right? Because just these things are new. You can in fact build anything, any of these 5 layers, if you just keep in mind the residual block and the extra features like this. There are other more fine nuances, and we will see how we code that. But the basic idea is this, that when you see a network, when you try to recreate a network from scratch, then you will see that you have to, from the architecture, you have to understand what are the blocks that are repeating, what are the new blocks, and you have to make new classes and just make the code clear that what exactly is doing. I would say I will make one residual block, and I would make another block with, no, I think I would make one residual block, and I will make another function that kind of looks into this number of blocks to be made, and also the it takes care of this filter size, right? This kernel's, the number of filters, sorry, not the filter size. And I think this will solve the issue. We will see how we do it in the next aspect, next video of how to code it from scratch. And but the basic idea to code is this, that you should understand what is a pattern, what is repeating over and over again, and understand what is the variable and what is repeating. And based on that, you make variables, you put it inside the model and learn and just code it, like just reduce the number of codes so that the for loop, it's kind of a for loop. It's like a for loop, right? You just make a function just for the for loop and see the pattern, just see what is being repeated, make that what is being repeated with the extra variables into a single function, and then apply that function over and over again by a single for loop, right? So essentially, it's nothing but a function that is being applied over and over again with the function with some certain parameters. Just define that function by the class and object-oriented programming, define that object, and then by a for loop, just input that into the actual ResNet, and you will get all the layers. In fact, you can, if you just, I'm repeating once saying, if you build just this to blue things, the blue highlighted things, and apply all these extra features, you can build any ResNet from scratch. So therefore, the most fundamental part is the blue part, and then this extra features, how to code it. And this is something we'll learn in the next video. I hope you enjoyed this video. I hope you learned something. You should read this paper like this. Any paper you should read, understand what's happening, and understand, read a bit of the periphery, other papers in the periphery that actually solves this issue. And then you will understand a lot about it. You have to give some time, and I hope this video help to understand how to read a paper, and also help to understand how to actually think about building an architecture from scratch, which is very easy. Okay, I believe it's very, very easy. So all the best, and I will see in the next video of how to build an architecture from scratch, this ResNet architecture from scratch, using this fundamental blocks and features. Understand that they have adopted batch normalization and after each convolution and before the ReLU. So a convolution layer, a batch normalization, and a ReLU. Okay. Okay, so all the best, and thank you, and I will see you in the next video. Thank you for staying till the end. Bye-bye.